I wish to welcome you to today's introductory colloquium on the science topics of one of the planned ECT STAR workshops for 2020. It has been deferred to 2021 because of the COVID-19 pandemic. The intention of this colloquium series is to introduce and publicize the science case of the workshop to a wider audience. Today's presentation, given by Catalina Cocciano and Christian Pischikia, both from LNF, INFN in Frascati, is on the workshop series STRANU, Hot Topics in Strangeness, Nuclear and Atomic Physics. That workshop had been planned to run during the week starting from July 2020. The talks focus on the role of strangeness at low energies, studied via kaonic atoms and nuclei at the Daphne Accelerator in Frascati. Let me briefly introduce the speakers to you. Catalina Cocciano received her PhD from the Institute of Physics and Nuclear Engineering in Bucharest with a thesis on the study of mesonic exotic mesons in the Obelix experiment at CERN. At the moment, she's a senior researcher at Frascati and leads a research group performing experiments both in Italy and abroad. Her main interest is in the strangeness aspect of nuclear physics and also in meson spectroscopy. Currently, she's the spokesperson for the experiment Siddhartha 2, which she will tell us about. Christian Pischikia, the second speaker, has received his PhD from the Università dei Studi in Rome, and his thesis work involved experiments on the lambda 1405 particle and the K-bar nuclear interaction within the Amadeus experiment at Frascati. There he is responsible for the data analysis, and he will tell us about the experiment today.
Hello to everybody. So I am here in Frascati, and together with my colleague Christian Pischikia, we are going to make you an introduction to the workshop which was supposed to be held in ACT STAR next week. And this has to do with the strangeness at low energies. You see here the title of the workshop, which we are now proposing to do and to shift for next year, probably in the second part of May. However, it's our pleasure to make an introduction to this workshop by picking up some selected items related with the strangeness at low energies. So what we are going to show you in the coming bit less than 1 hour, it's some studies of low energies strangeness performed by doing kaonic atoms experiments and also kaon nuclei interaction studies at the collider we have right here in Frascati, which as many of you probably all know, it's called Daphne. So the story of the kaonic atoms, it's a story which started many years ago. Actually, there are nearly 40 years that kaonic atoms are being studied. Initially, the studies were very, very difficult because the technology, including beams, available kaon beams, were not so good as we have today, but also detectors evolved meanwhile, which means that we were able to go from something which looks like this, where the kaonic transition lines are almost not visible, to something which looks much better, with experiments which have been done both in Japan and also in Frascati. So just to show you what has been the progress, look here. So now we have clearly seen the kaonic transitions in hydrogen here to the fundamental level, and later in Siddhartha here in Frascati. And just a brief refreshing of the mind of the scientific case, the kaonic atoms are a very important tool to study the strong interaction at very low energy, practically at threshold, because the physics of the formation and of the decay, namely the transitions, of the kaonic atoms from a highly excited orbit, which is formed when the kaon is initially captured after being slowed down, replacing the electron, well, it's based on the fact that, as we all know, the mass difference is a factor nearly 1,000. So the kaon is captured in a highly excited state, and part of the kaons succeed to make it to the 1s level, to the fundamental level, of course, emitting radiation, which in this case it's in the X-ray regime, so energies which are in the level of few, even 10 or hundreds of kilo electron volt, depending on what the nucleus is. But the most interesting feature which makes them suitable to study the strong interaction is the fact that when the kaon gets to the fundamental level, there is a possibility to study the strong interaction, since this level suffers the strong interaction with the nucleus. So on the top of the QED, which actually leads the formation of the kaonic atom and actually the energies of the level, there is superimposed the interaction, which is the strong interaction between the quarks in the kaon and those in the nucleus. And this interaction actually shifts the level with respect to the QED level, calculated values, and also it's broadening this level because the lifetime is very limited, since the kaon itself it's eaten up, so it ends up by a strong interaction with the nucleus. So we have explicitly a shift and the width with respect to the QED calculated values, which we can then derive by measuring the X-ray energies of the transition to this fundamental level. This is more or less a scheme which says the same things, namely that the 1s level, the fundamental level in the kaonic atoms, are suffering a shift and the broadening with respect to the electromagnetic interactions, which are easy to be accessed if one succeeds to measure the transitions, namely the K series, to these kaonic atoms. So this is what we are aiming for, and in order to do this, of course, we need to form the kaonic atoms, and we also need to measure with as possibly high precision as we are able to the X-ray transitions to this level. And if one is able to do this, then, so namely to measure the shift and width of the kaonic atoms, starting with the lightest one like hydrogen and deuterium, we have also performed some kaonic helium measurement, but here we didn't yet reach the fundamental level. We had to stop to the 2p level. I'll come back to this shortly. One is able, namely the theoreticians are able to extract the isospin-dependent kaon scattering, nucleon scattering length. And this is a very, very important quantity, even more so lately, because as you know, you will see shortly, this is also related with the equation of states of neutron stars. So this is more or less what I was saying. So experimental quantities are shift and broadening of the fundamental level, which are then connected with the scattering lengths of the isospin-dependent anti-kaon nucleon interaction. And of course that in order to extract this, it's not so easily. So the recipe which has been put forward up to now relies on the formula which takes into account also some isospin breaking correction. And for the moment, this formula, it's reliable enough for the experimental precision, which has been reached. But of course, what we hope is that in the near future, we will be able to perform even more precise measurement. So this formula hopefully needs some further calculation and refinement. But that's, let's say, the interplay between the theory and experiment, which deals with the kaonic atoms. Okay, then what happens next? When we have this very important information like the scattering lengths for the strangeness physics, like anti-kaon nucleon interaction, then one can make a step forward and address items which have to do, which are strictly connected with the chiral symmetry breaking, explicit and spontaneous, in systems with strangeness, which are peculiarly interesting because They are referring to a strange quark, which has the mass intermediate between the small quarks masses, like so light quarks and heavier ones. So it's very interesting to study this. And one also addresses items which have to do or might be important for neutron stars, to a very hot topic today. And this will be addressed after me, the dense baryonic matter, so nuclear physics with strangeness. So we all know that the strangeness plays an important role in particle and nuclear physics. It's yet an open issue. What is the role played of strangeness for the universe? Like, again, I repeat myself, inside the neutron stars, for which yet it's not very clear what it's the heart of a neutron stars. And even if there is the possibility to have more type of families of stars, some are quark, might be quark stars, or neutron stars. So this is an open issue which needs information coming, of course, from astronomy, gravitational waves included, but also it's very important to have information coming from labs like ours and experiments which measure at low energies, so at threshold. Of course, we would like to also access information below threshold, and Christian will tell you more about this just shortly. And in order to be able to distinguish between this plethora of equation of states, this is not even recent, so meanwhile might be even more nice equation of states which have been put forward. So that's an open issue, and there are many researchers working on this to try to figure out whether a neutron star is a neutron star and that's all, or it might be placed for strangeness, and if so, in what type of form. And well, when you measure kaonic atoms, as I told you, you access the information at threshold. This is a slide prepared time ago by Wolfram Weise, which shows, for example, how nice this information already obtained by Siddhartha, it's constraining the scattering amplitude. In this case, it's chiral symmetry calculations, and how important it is. Also tells us as experimentalists that if we would be able to constrain it even further, that might be important, because might constrain the door between the above threshold and what happens below threshold in a very nice way. So when we do our experiment, well, there are many places in the lab, and we all hope that in the STRANU workshop next year, this will be all put together in a friendly and collaborative effort towards real progress in the field. But for what we are concerned in this evening, by no way, absolutely by no way being this the unique place where we do this type of research, but it's one of the most important, namely the Daphne Collider in Frascati. So Daphne, it's a very nice machine, which actually it's a complex of accelerators containing a linear accelerator, you might see here, a damping ring where electrons and positrons are packed together, and then a double ring where electrons and positrons are smashing one against the other one, colliding at the precise energy of the phi resonance. So we are producing about 1,000 phi resonances per second, which decay in 50% of the cases in very slow momenta, so slow, small energy, kinetic energy, charge kaons, which is a very interesting and nice that we have a pair of kaons, because then we can use the fact that it's a back-to-back process to be able to trigger on the very interesting physics which we care about. So that's the machine as it looks. That's schematically how electrons and positrons collide to deliver the phi resonance, delivering in turn the very slow energy momenta, 127 MeV over C, which is important because this tells you that in order to stop them, if you want to study kaonic atoms, this is rather easy. You don't need meter-long degraders. It's enough to have some millimeters of plastic foils, and you don't screw up the quality of your beam if what you're chasing it's a kaonic atoms physics. So we use these kaons delivered at Daphne then to study the kaonic atoms, and as Christian will tell you after me, to also study not only atomic physics, strange atomic physics, but also the nuclear interactions with strangeness. And we have pioneered this years ago with Siddhartha experiment as already a second phase coming from there, but I'm not going to bore you. It's all the history. I'm only going to show you that this is a very active field and rather broadly international, because you see how many institutes are participating, with also some European funding in the past and in the present. And we have used also pioneering cryogenic targets, so still gas targets, so not liquid, where you have additional phenomena which are dumping the signal, like the Stark effect. So you want better to use the gas, but you want to use a dense gas, and this we obtain by using specially developed cryogenic targets by Hannes Mescal from Vienna. And around these targets, which look more or less like this, so this is the container, it would be a whole story, very fascinating, but I will jump over it in spite of the fact that I feel tempted to tell you more. So please, those who participate at STRANU next year, just ask me when we will meet next year, hopefully. And we also needed to develop the detectors, which are measuring X-rays, but are also fast, in order to be able to trigger on the back-to-back kaons delivered by Daphne. We actually developed by ourselves in the framework of our European project silicon drift detectors for spectroscopic purpose, which are rather large area for this type of application. So 1 square centimeter packed in the framework of Siddhartha 3 by 3, and we put them around the target you have seen before. Again, I don't want to bore you with technical information, but they have a very special geometry, which relies on an anode which has a very, very small area, which actually, as you might have guessed, it's proportional to the noise, so they have a very good resolution. We put these detectors around our target, 144 of them, to measure the X-rays delivered when we had a signal from a trigger which told to our SDD detectors, read the signal now, because this is in a coincidence with a K plus K minus pair coming from the decay of the phi particle produced. So that's how it goes. We produce phi particles which decay K plus K minus, stop K minus inside the target, deliver the X-rays from the kaonic atoms, which are measured by the silicon drift detectors. These are nice pictures taken kind of 10 years ago. You might recognize here again Hannes Mescal, and that's not really a picture, but it's a schematic view of our setup inside the Daphne in 2009. This is Siddhartha, and that's us by that time when we finished this measurement, which was very, very well. On one way was a very challenging measurement. The other one was very satisfactory, because we succeeded to do measurements like kaonic helium, finally resolving once forever, washing out a puzzle which was hanging around for many years, generated by very imprecise measurement performed in the 70s and 80s, with the most which people could do by that time. So that was measurement which hinted towards the fact that there is a shift on the 2p level, be aware, 2p, where nobody expected to have a shift there. Actually, the puzzle, or let's say the puzzlement situation, was that the shift was predicted to be 0, while measurements showed kind of evidence that could be high with respect to 0. This has been solved already by early 2000 by a measurement performed at in Japan at Keck, which has shown that probably there was some problem calibration or whatsoever, but now the situation moved towards a measurement which you see here. This is helium-4 performed at Keck. We also, in 3 days, only 3 days, succeeded to measure. I'm not going to bore you with this slide, but so our aim with Siddhartha was to measure hydrogen. Also deuterium, but deuterium we did not succeed by that time. We are anticipating we are hunting it right now in the framework of Siddhartha 2. But to have some let's say calibration, we also use helium-3 and helium-4. You see this here, it's the target type, and on the other axis we have the time. So this is the months, January until November in 2009, and the type of the target and the time dedicated to the target. And as I told you, we went for the hydrogen, but we also did some helium. You see here our first measurement of helium, the L transition, so for the 2p level, and so on and so forth. We also did for the very first time, so the first measurement of helium-3, because one interesting thing is to measure, if any, isotopic shift between helium-3 and helium-4. And we succeeded to get a very nice precision measurement, so for statistics systematics errors in electron volts, and that's the situation now. So you see we are going to a precision era, and that's what the publications we have done by that time. So we measured helium-3 and helium-4, and that was one of the achievements. The other one was the hydrogen, of course, which we measured, and we clearly identified the K transitions, so the K complex to the 1s level, which we analyzed together with the deuterium, where we didn't see transitions, so we used that for estimate of the background in the simultaneous fit method. So we extracted the K complex transition lines, which you can see here in this slide, and we have published them already in 2011, being this the best measurement, the most precise measurement to date, which we still would like to improve. And we would like to improve because this is exactly the measurement I showed you in the slide of Wolfram Weise, which is right now used to tune the door between above and below threshold. And of course, if you succeed to close it even more, you might have even more precise predictions of what's the physics around. I put it here, so for those who are interested, a list of the papers which show our results for hydrogen, deuterium, helium, and even more. And what now? Now what we are left with is the conic deuterium measurement, which is much more challenging than hydrogen, if not for else because the yield, so the yield of this transition, it's about a factor of 10, could be even more, smaller than the one of hydrogen. So these are the theoretical predictions in terms of shift and width of fundamental level of the deuterium with respect to the QED. And you see that they are spread all over, so there is no consensus of where you should look like. This makes for us the thing very challenging. And to pick up this challenge, we went through a new collaboration, so Siddhartha 2, which is relying on the skeleton of the previous one, but with some new elements of new institutes added to the collaboration. And basically what we are doing right now was to practically change everything. Initially, we wanted to only change few elements, but in the end, we have changed all, from targets to detectors, additional 2 veto systems, trigger systems. So we have developed a new array of SDDs, which if those who are careful among you might already notice that the overall area has a much higher ratio between the active and total area. So 90% with respect to 40%, which of course increase the same rate, the total solid angle, so the efficiency of your apparatus. And these are some details, look similar to the previous one, but as I told you, it's very, very much enhanced by signal over background due to the few innovations, including veto systems staying outside, which are vetoing particles coming from outside, which are background particles coming from the lost beams inside Daphne. We have installed our apparatus inside Daphne in 2009, so last year. We were now in the status of optimization when COVID has arrived, so we had to stop. We will restart again in autumn this year with the plan, if everything, let's cross fingers, go fine, to do the conic deuterium measurement. You see here a Monte Carlo simulation with our aimed precision, which is similar to the hydrogen one. And that's what we are aiming for, which should put us on the chart of the width and shift in this context with this kind of rectangle. We don't know, of course, where it is. It might be here, it might be here, or it might be here, or it might stay where we put them, where there is no theoretical prediction. So everybody's looking for this measurement. Of course, we as a first stand. We have additional future plans, and for those of you who are watching, we need your help and contribution, because among these future plans, there are proposals to extend our scientific program by performing additional precision, very high precision measurement of conic atoms, both those not affected by strong interaction, so transitions far away from fundamental level, dictated only by the QED, aiming to measure the kaon mass, or departures from the QED, and maybe other conic atom transitions which are being requested by the scientific community, including some K+ physics like scatterings and so on and so forth. So we are preparing our detectors, including a spectrometer which is extremely high precision, using a crystal which is a pyrolytic graphite crystal, which is able to reach resolutions which are extreme, like electron volt level resolution. So at least factor 10 better than present detectors. So we are aiming to do this. And this is my part. I'm ending here the part of the conic atoms with the message: we watch you, we need your community and theoretical physicists to tell us even more what you need from us and how can we be of use for entire community, by also stating and indicating this paper in Review of Modern Physics from published last year, where we conclude in that paper that the modern era of precision measurement of conic atoms, it's really fostering a deeper understanding of the strangeness interaction at threshold. And this has huge implications, which are going from extend from particle physics up to astrophysics. I do the acknowledgement now, acknowledging all these funding agencies and projects, including STRANG-2020, and for this we also thank to the ACT STAR, of course, for allowing us to be with you. So thank you to the director, Jochen Wambach, and to everybody there, to Barbara and to all the staff, allowing us to reach you in spite of the difficult situation. So I leave floor to Christian, who's going to tell you another story related with the nuclear interactions. So I'm going to share another file. Christian.
So, hi everybody, I'm Christian. I will move from Siddhartha to another experiment performed by our group, which is called Amadeus. So the link between the two is very simple, in the sense that Amadeus follows the fate of the K- after the capture in an atomic level, after the cascade. When this negative kaon starts to feel very strongly the strong interaction with the nucleus, it is absorbed. So the aim of the experiment is to get information essentially in order to solve the well-known puzzle of the lambda 1405, which is strongly related to the possibility for the formation of even more fancy K- multinucleon bound or quasi-bound states. And also clearly, as I will show, to give newer, more precise information about scattering amplitudes and cross-sections. Very hot topic nowadays, related, of course, to the possibility of bound state, is also the formation of K- multinucleon absorptions. And all of these, as very nicely introduced by Catalina, have, of course, strong implication in astrophysics, in particular for the physics of neutron stars, and clearly, more fundamentally, concerning the origin of the hadron mass related to restoration, partial restoration of chiral symmetry. Okay, so to be a little bit more precise, I also show here, you can see the present status of calculation concerning the real and imaginary parts of the K- proton scattering amplitudes from the chiral models which are presently on the market. Now, as we saw before, at the threshold 1432 about, all the models converge to the same point. This is exactly due to the very nice and precise measurement which is performed by Siddhartha, which is a measurement at the threshold, let's say at zero momentum of the kaon. Now, what Amadeus can do is to give information below and above the threshold. So, as you can see here, for example, in K- proton, the situation below the threshold becomes dramatically different. So, the models can really predict different results. And this is related to the lambda 1405 itself, to the position and the width of this debated state. What about above the threshold? Above the threshold, experimentally, the constraints are given by K- proton scattering data. And as you can see here, I compare, for example, the result of a chiral, namely the so-called Kyoto-Munich model, with a phenomenological calculation. The two are in quite well agreement as long as you are near to the region where experimental data exist. But as you can see, as you approach the threshold, more precisely, when you go, sorry, just a second, when you go below 120 MeV over C of momentum of the kaon, there is a complete lack of data. Now, this in particular is a measurement which is ongoing by our group. I hope to report next year when we will see live at the workshop. This result would be really important, in particular for exploring the nature of the lambda 1405, because it gives in sigma 0 pi 0 and lambda pi 0 the two counterparts of the isospin almost purely 0 and 1 amplitudes. So, below the threshold, as I told you, in K- proton, for example, there is not presently direct amplitude measurements available. And what about K- neutron? As we heard before by Catalina, this is an essential information which will be given by the measurement of kaonic deuterium at the threshold. And as I will show you, Amadeus can give the same information just below the threshold. As you can notice, with respect to the K- proton plots, in K- n, the situation is even more dramatic. First of all, because we don't have at the moment, before Siddhartha 2, any constraint at the threshold, but also below you see that the situation is quite dramatic among the different chiral models. So, some few more words on the lambda 1405. As you probably know, this is a state, an isospin 0 state, whose position and width cannot be fitted within a simple three-quark model. And in the last year, it is quite well accepted that it can be partially a K-bar-N quasi-bound state. In chiral models, for example, this is interpreted dynamically. It emerges at two poles in the scattering amplitude. So it should be somehow a superposition of a quantum state which is much broader and at lower energies, around 1380 in mean, which is mainly coupled to the decay channel, to sigma pi, and a narrower and much higher mass pole, around 1420, 1430, which is indeed mainly coupled to the K-bar-N channel, which already tells you that if you would like to distinguish this narrower and higher mass pole, for sure you have to produce the resonance in what is called the K- induced reaction, in K- proton capture, for example. Related to the nature of the lambda 1405, I mean to the strength of the K/N interaction, in particular in the isospin 0 channel, is the possibility for even more fancy states, K- proton-proton, or even more nucleons were predicted, but let me concentrate on K- pp. Here the situation is even more dramatically unclear. Here is summarized what we expect from the theory, binding and width. You see also from the plot that the situation is really unclear, and the findings of experiments in various production channels for the bound state. Now, in the last years, what is clear is that the situation is unclear. In the sense that, first of all, theoretical interpretation of the data is strongly dependent on the K/N input model and on the production mechanism. Very interesting, let me mention the recent measurement by E15, I mean the second run, which was interpreted by Sechiara, Oset, and Ramos. In this case, a K- pp was observed with a binding of a little bit more than 40 MeV and broad width of 100 MeV, and was produced in K-induced reaction at very high energy. The kaon has a momentum of about 1 MeV. Okay, very different from our situation. So the goal of our measurements, as I told you, are to extract information on the lambda 1405, and this is that and other resonances, of course, which is given, which is obtained by correlating the hyperon pion production. The same if you want to measure cross-section. This is presently ongoing. And the puzzle of the bound state and kaonic multinucleon absorption, which is investigated by means of hyperon-nucleon or multi-nucleons correlation. The future, which I'm really strongly confident we can give important experimental information, which follows indeed from the story of the hyperon-multinucleon interaction, in the sense that after a primary production of the hyperon, if you produce it in a light nucleus, the hyperon can have final state interaction, can rescatter with the residual, and this can give very important information on the single or multi-nucleon scattering cross-section of hyperons, which are totally crucial for the equation of state of the neutron stars. So we already heard about Daphne. I just remind you that the crucial point for our experiment is that the kaons have a very low momentum. They start with a momentum of 127 MeV. What we do presently is to use the data collected by the Chloe detector, using Chloe as an active target. Chloe is quite simple detector. It's a big cylindrical drift chamber with very good acceptance, which is surrounded by a calorimeter, which means that we have information both on charged particles, but also on gammas and also on neutrons. What sense the detector is active? You can see at the center of this picture the interaction point of Daphne, and if you follow the path of the K-, for example, you will encounter as first the pipe of Daphne itself, which is mainly beryllium, then the inner wall of the chamber, which is carbon, and then the gas which fills the chamber, which is a mixture of helium, carbon, and hydrogen. Okay, so we use the interactions themselves of the kaon with these materials in order to study the nuclear absorption of these kaons. The result of this is, of course, an excellent resolution in momenta and energy. So, moreover, we take advantage of the fact that we have two completely different physics of the absorption of the K-. The absorption at rest is the case of Siddhartha. It was I was telling you before. So, this kaon, imagine that the kaon enters the gas, which fills the chamber. It is slowed down to very low momentum. At some point, it is captured in a high-level atomic orbit. It cascades down. At some lower lying level, it starts to feel the strong interaction with the nucleus and is captured. It is captured with the momentum, which at the nuclear scales is zero, essentially. But since Chloe itself was designed at the beginning to let the kaon cross the detector, we have a huge flux of flight captures. In this case, the kaon crosses the electronic cloud without being captured and hits the nucleus directly with a momentum which is 100 MeV. This is just before a bit of degrade, due to crossing the materials of the detector. So just to link directly to the previous slides of Catalina, I start from the measurement of K- neutron into lambda pi minus, which is the first measurement of the scattering amplitude below the threshold. How do we go below the threshold? This is very simple. We use a nucleus, helium-4 in this case, and we capture the K- on a bound neutron in this case. The binding energy of a neutron in helium-4 is of the order of 20 MeV, which means that you are exploring the interaction just 20. To be correct, there is also the kinetic energy which is carried away by the spectator, helium-3 in this case, okay? So you are investigating the interaction 20 plus about 10 MeV below the threshold, okay? So this is a summary of the sample of lambda pi minus which we detected. We performed a simultaneous fit of many kinematical variables. But let me concentrate on the invariant mass of the detected lambda and pi just to explain you which was the goal. So you remember a few slides before that I showed you chiral predictions for K- and scattering. This calculation was performed in S-wave. S-wave in this channel means non-resonant. Non-resonant because below the lambda pi you can just create for isospin conservation a sigma 1385 resonance. The sigma 1385 is spin 3/2, which means that you can only access P wave. So what we have on the market for the theoretical models is non-resonant, and we wanted to pin down one or more of these models. Okay, so experimentally, what does it mean? We had to distinguish this blue guy, which you recognize from the invariant mass to be the sigma 1385 resonance, from this red guy, which is the non-resonant, also called quasi-free formation. What does it mean, quasi-free? It means that you come from the inner channel K- neutron to the final state lambda pi minus without going through the resonance. Okay? We just wanted to extract the yield of this channel. We succeeded in that, and the gray band you can see in this plot is our measurement, namely the non-resonant transition amplitude Kn into lambda pi, which is compared with the amplitude, so the square root of the square of real and imaginary parts, which I showed you before, for the various models. As you can see, we are in very good agreement with Barcelona, with Kyoto Munich, and within a little bit more than 1 sigma also with Prague. The next step, in order to give some information on the lambda 1405, would be to analyze the corresponding sigma 0 by 0 channel. This is because the lambda 1405 is isospin 0. This is quite a difficult item, just because the resolution for the 3 gammas which are involved in this channel is much less with respect to lambda pi minus. To compare, I can tell you that for lambda pi minus we have a resolution in mass which is of the order of few MeV. Here we are of the order of tens of MeV. Nevertheless, we have the possibility to use this very nice production of these flight captures of the kaon, to try to pin down the higher mass ball of the lambda 1405. Why does we have to use the flight capture? For the same kinematical reason which I was telling you. If you capture a K- on a bound proton, for example, in carbon or in helium, you have to take into account the binding energy of this proton, about 20 MeV, which closes the possibility for observing a high mass pole of the lambda 1405, which is expected by chiral calculations to be about 1420, 1425. Thanks to the additional energy, which is given by a flight kaon with a momentum of 100 MeV, which traduces in mass in a gain of about 10 MeV, indeed, in the flight component of our data, we see, is evidenced here, something which is sitting around 1425. Now, the last step in order to clearly identify the resonance in this plot is to disentangle, as before, the non-resonant component in the formation of these final state sigma 0 by 0 pairs, and this is exactly the work which is now ongoing. Now, I go to the item of the multinucleon and bound state of a kaon with more nucleons. I told you before that this topic is very hot. It's hot essentially because recently, and I quote here some theoretical calculation on this item, it emerged that indeed we have a very rich database of kaonic atomic data, no? But what emerged is that we cannot understand this data without a multinucleon absorption term in the optical potential. For example, you can see here the result by Friedman and collaborators. The Kyoto-Munich and Prague model described the fraction of single nucleon absorption, which means that it is not the global amount, when you put a multinucleon term in the optical potential, which is calculated in this case on the base of a phenomenological model. It is then clear that you should experimentally disentangle and measure branching ratios, which are not available presently, which were not available, and cross-section possibly for the 2, 3, and 4 nucleon absorption processes. As for what concerns the K- proton-proton bound state, in K- induced reaction, namely the same reaction we explore here at Daphne, there are two results which are very interesting. Finoda, probably you well know, on the same machine, Daphne, measured in K- proton-proton this spectrum, which they interpreted as a bound state with a very high binding energy and very narrow width. At Ki, the red distribution, which is in between the disentangled 2 and 1 nucleon absorption, was led to the interpretation of theoretician essentially as possibly a bound state with a binding energy, which is essentially the difference between the threshold and the mean of this distribution, but also something else, because this leaves really the space, the window for the multinucleon captures, which were not known at that time, and also conversion processes. With conversion, I mean when in the first step of the interaction, a sigma hyperon is produced, this scatters on the residual and goes into a lambda particle. So this is again the sample of what we measured. We exploited the absorption of a K- onto carbon-12, and we wanted to disentangle correlation of a lambda, a proton, and the residual. This is the simultaneous fit, again, on the various dynamical variables, from which we obtain this nice table, which will really serve to the theory in the future, in which for the first time the 2, 3, and 4 nucleon absorption were disentangled, and the branching ratios and cross-sections for almost all of these channels were measured. Let me stress that, for example, for the 2 nucleon absorption, we succeeded to disentangle the quasi-free, so without final state interaction, from 2 nucleon with elastic or inelastic final state interaction. Moreover, in this work, we gave some other interesting inputs. The first, we asked, okay, let's try to calculate the ratio among the production of lambda proton and sigma 0 proton. Given the fact that the sigma 0 decays in a lambda and the gamma, we also succeeded to obtain the relative yields of the sigma, as you can see in these plots. Okay, so you would expect from the phase space that this ratio is bigger than 1. Indeed, is 1.22. It's easy to calculate. But what you find is that it is much less. It's 0.7. This was very recently calculated in the context of two chiral models, Prague and Barcelona, and indeed gave very interesting information. You see that only if you pin down the correct density and you take into account for the nuclear interaction, essentially the Pauli blocking here is dominating, only in this case you can access the experimental result. Otherwise, for example, in free space, you are totally out of the measurement. Now, in this work, also for the first time, the two nucleon absorption global in all the possible channels was calculated by Hartankova and Ramos. And this is very interesting to update the result for the interpretation of kaonic atomic data. But of course, experimental test of this calculation is strongly needed. From the table I showed you before, so if you absorb a kaon on two nucleons, you have many final state hyperon nucleon which are possible. The calculation, which was performed by Hartankova and Ramos, gives a global branching ratio of about 15%. Now, if you sum up all the two nucleon absorption which we measured, with or without final state interaction, you end up with 16. This is a good estimate of the global two nucleon absorption capture branching ratio, just because you may wonder, okay, but you just measure lambda proton and sigma 0 proton, so how can you tell that? Because if you explore in detail all the possible final state elastic and inelastic processes which we measure in our experiment, you realize that at the end you almost always have a lambda and a proton in the final state which enters in our acceptance. Okay, this means that in this table we measure all the processes essentially except for these four which I list here, sigma minus n and so on, for which we succeeded based on our measurement and all the information which is available from bubble chamber measurements to give the total missing ratio, which is about 5, which means that globally the net total K minus 2 nucleon absorption branching ratio is estimated by us to be about 21.6. So you would wonder why you said nothing about the bound state till now. Why you hide it? Because it is hidden indeed in our measurement. What we realized is that in this situation, K minus induced reaction at very low energy with respect to E15, the bound state is completely hidden below the two nucleon absorption. At the right of the data, you can see, for example, simulation for a binding which is similar to the one which was found at E15 for different widths. You see that despite assuming a really unphysical and narrow width, you cannot at all distinguish the two nucleon from the bound state, essentially because the nuclear form factor in this kind of kinematical situation dominates. The quasi-free production dominates totally. To confirm this, we repeated the same analysis, a similar analysis to what was done by Finoda. The essential cut operated by Finoda was an angular cut to pin down the back-to-back production of a lambda and a proton. If we apply this cut to the previous sample, which I showed you, we obtain indeed a spectrum which is extremely similar to Finoda. Finoda was dominated by carbon plus a few other targets. But the main difference is that repeating the analysis in the same way, we can completely describe our spectrum in terms of multi-nucleon absorption processes, and we obtain exactly the same branching ratios as for the whole sample, so without really the need of a bound state. I conclude in a few minutes with a another and very elusive state, which is the 4-nucleon absorption, which you can investigate through the correlation of a lambda and the triton, and for which the golden target is for sure helium, 4 nucleons. In this case, in literature, we really have nothing or very few. We have 3 events from an old bubble chamber experiment, and from FINUDA, we have 40 events from combining all the targets, from which they succeeded to obtain a global, no 4-nucleon, a global yield, which is estimated to be of the order of 10 to the minus 3 for stop count. So if you see here at the left, this is the global sample of tritons, which we really photographed. So this is clearly tritons. You see here the first peak is proton, the second deuterons, the third is tritons, just because we succeeded to measure the mass of the tritons by the technique of time of flight. So the signature is extremely clean, and in this fit, which we are going to publish soon, left you see our sample in helium, which is, as I told you, the cleanest, the golden channel. And in particular, what we obtained and what has really a kinematical signature which is totally closed is the K- absorption of 4 nucleons in flight, from which we got the first measurement of the cross-section of this process. We used also carbon for having confirmation of this cross-section, which is quite fine, and from which, similarly to the lambda proton analysis, which I showed you before, we also got the same cross-section for the sigma 0 triton 4-nucleon production. So I thank you. In this last slide, I summarize our recent published or ongoing results, and I really hope that Catalina and me encourage you to follow, to come to this workshop, which hopefully we will have next year, and we interested you on this topic. So I thank the ECT STAR in particular for giving us this opportunity. Really, I think that this is a very nice thing in this difficult period. So from my side and Catalina, bye and see you soon.